A very good morning to one and all. In this video, we are going to discuss about taxonomy for wearables. So, to begin with, the wearables can be classified as single function or multifunctional. They can be also classified as invasive or non-invasive. It can be also classified as active or passive based on their types, and based on their deployment mode it is classified like that. Based on the communication mode it is classified as wired or wireless, and it can be disposable or reusable. Wearables also classified based on the field of use. For example, health, public safety, entertainment, military, information processing, acoustic sensing, pressure sensing, position tracking. What is mean by invasive wearables? The invasive wearables can be further classified as minimally invasive, those that penetrate the skin to obtain the signal, or as an implantable such as pacemaker. Implantable sensors require a hospital procedure to be put into place inside the body. Next one, non-invasive wearables. It may or may not be in physical contact with the body. The one not in contact could either be monitoring the individuals or the ambient environment. Non-invasive sensors are used in systems for continuous monitoring because their use doesn't require extensive intervention from a healthcare professional. Example, a camera for capturing the scene around the wearer, or gas sensor for detecting harmful gases in the area. Non-invasive sensors are typically used in the systems for continuous monitoring, right? Wearables can also be classified based on their types as active wearables or passive wearables. Active wearables are the one which requires power to operate. Example for this one is pulse oximeter. Pulse oximetry sensors fall into this category, right? Next, passive wearables. What is the one which doesn't require power to operate? The example for this one is temperature probe. Another view of wearable is the mode in which the signals are transmitted for processing. It can be either wired or wireless. The signals are transmitted over a physical data bus to a processor. It is called wire, right? In the wireless class of wearables, the communication capability is to be built on, which transmit the signals wirelessly to a monitoring unit. The sensors can be for one-time use or they can be reusable. Wearables can also be classified based on their application. It ranges from health and wellness monitoring to position tracking, etc. The proposed taxonomy serves two key functions. First, it helps in classifying the currently available wearables so that the approximate one can be selected depending upon the operating constraint. Second, it helps in identifying the opportunity for the design and development of newer wearables with performance attribute for specific areas that need to be addressed. Next topic, flexible electronics. It is another class of wearables. It is focused mainly on printing electronics. Example, thin film transistors, thin metal film, nanomaterials and carbon nanotubes. Next topic what we are going to discuss is wearable ground reaction force sensor, in short GRF. Ground reaction force. It is a force exerted by the ground on a body in contact with it. For example, a person standing motionless on the ground exerts a contact force on it that is equal to person's weight, and at the same time an equal and opposite ground reaction force is exerted by the ground on the person. The ground reaction force GRF coincides with the notion of a normal force. However, in a more general case, the GRF will also have a component parallel to the ground. For example, when the person is walking, a motion that requires the exchange of horizontal frictional force with the ground. The use of the word reaction derives from Newton's third law, which essentially states that if a force called action acts upon a body, then an equal and opposite force called reaction must act upon another body. The force exerted by the ground is conventionally referred to as the reaction. Although, since the distinction between action and reaction is completely arbitrary, the expression ground action would be in principle equally acceptable. The component of GRF parallel to the surface is the frictional force. When slippage occurs, the ratio of magnitude of the frictional force to the normal force yields the coefficient of static friction. So now let's come to the main topic called wearable ground reaction force sensor systems. A wearable GRF sensor system was constructed using 5 small triaxial force sensor. It named it as USL 06H5 500NC. It weighs around 15 gram and the size is 20 mm cross 20 mm cross 5 mm. It was made by Tech Jihan Co. Japan. The GRF and COP measured using the wearable sensor systems were expressed in a global coordinate system which was located on the interface between the instrumented shoe and the ground. The origin of the global coordinate system was fixed to a point around the anatomical center of the ankle when the sensor system was worn on the foot. The x-axis was shown to represent the anterior-posterior direction on the interface plane contacting with the floor, which was based on landmark from the shoe. The z-axis was made vertical and the y-axis was shown such that the resulting global coordinate system would be right-handed. By mounting the 5 triaxial sensors on an aluminum plate beneath the shoe, we can accurately align all 5 local coordinate systems defined for each triaxial sensor with global coordinates fxi, fyi and fzi, and I is equal to 1, 2, 3, 4 and 5, which indicate triaxial force measured by the distributed 5 triaxial sensors, and xi, yi is defined as the position of each triaxial sensors. For example, x5, y5 indicates the position of the sensor placed on the forefoot. The total weight of the sensor shoe is about 300 grams and the shoe size is 250 millimeter. So the first diagram, it indicates, that is A, definition of sensor coordinate systems and sensor mechanism. So these are the 5 sensors which is showing fy. For the second sensor, it is showing fx2, fy2, fz2, and I have already defined what is fx2, fy2 and fz2. Likewise, for fifth sensor, I have indicated as fy5, fx5, fz5. So these are my 5 small triaxial force sensor which is placed at the bottom of the shoe under the soft rubber material, which is about 15 millimeter in size. The second diagram, that is B, it shows the prototype of an instrumented shoe for right foot. GRF's time sample matrix G of t consists of a force vector f of t composed of 3 components, fx of t, fy of t and fz of t, and COP coordinate function of p of t, which gives 2 coordinates x and y. Referring to the global coordinate system of the sensor system, G of t is equal to fx of t, fy of t, fz of t, px of t, py of t. So let me take that one as first equation, where t is t on, t off, on off, subscript mark the beginning and end of the fruit flat phase of gait. To analyze all the successive foot flat phase in a walking trial, two necessary conditions for detecting periods of heel and forefoot contact were applied to the vertical force component Fz1 of t plus Fz3 of t, obtained from two triaxial sensors on the heel, and Fz5 of t obtained from triaxial sensor on the forefoot. In this study, the mid-stance phase, during which the heel and forefoot are in contact with the ground, was evaluated to analyze extrinsic gait variability. All three phase components of GRF and COP coordinates in the foot flat phase could be easily calculated by using triaxial force measured using 5 triaxial sensors. The calculation method is similar to that of our previously proposed measurement system. A multi-channel data logger was specially designed using a microcomputer system for the sensor systems, and data from the sensor system could be saved in SRAM, static random access memory, at a sampling rate of 100 Hz. Algorithm for evaluating extrinsic gait variability was made using MATLAB software. The offline data analysis was performed by uploading data saved in the SRAM to a personal computer through a RS-232 communication module. The small triaxial force sensor integrated in the shoe and the portable data logger based on a microcomputer systems were all low energy consumption devices. So the wearable sensor system could be powered using a 300 milliampere hour battery. A wearable GRF sensor system is used to measure COP and triaxial GRF in a number of walking trials which was developed, that is shown here. The natural gait was almost never affected by the sensor system in the ambulatory GRF measurements. These are my reference for this entire video. The first one is Fundamentals of IoT and Wearable Technology Design, IEEE Press, Wiley Higher Road. Second one is Wearable Sensor Fundamentals, Implementation and Application, edited by Edward Sesonova, second edition. The third one is a wearable ground reaction force sensor systems and its application to the measurement of extrinsic gait variability by this author, Department of Intelligent Mechanical System Engineering, Kochi University of Technology, 185. This is difficult to pronounce, Japan. So in the next forthcoming video, we are going to see about the second unit of this subject. So till now we have discussed about the first unit of the subject. So in the forthcoming lecture we are going to see about the second unit of this subject. Thanks for watching this video. Thank you one and all.